Good morning, class. Here's chapter 5, integrals, and section 5.4, the substitution rule. So we covered the FTC, fundamental theorem of calculus, and now the substitution, reminding you of various basic integration formulas that we have seen. Power rule, exponentials, sinusoidal functions, various trigonometric functions. And now we are adding FTC. There are two of them. In short, the integral of a to x f of t dt, when we differentiate, we get the function back, f of x. And the integral of a to b f of x dx, the definite integral is a number, capital F of b minus f of a. And now the substitution, which we are going to go over right here. So what is the substitution method? Integration by substitution is the reverse process of the chain rule in differentiation. So let's differentiate this composite function capital F of g of x. So it becomes capital F prime of g of x times g prime of x. Now, normally capital F prime is lowercase f, so we can replace it with f of g of x, g prime of x. Therefore, if I integrate the right side times dx, of course, I get the left side, capital F of g of x. It's just a simple proof. And so let u be g of x, then du dx is g prime of x, and du is g prime of x dx. The integral of f of u du is capital F of u plus c, or capital F of g of x plus a constant. Over any interval for which u equals g of x is continuously differentiable and f is continuous on the range of this function, the following relationship holds: the integral of f of g of x, g prime of x dx, where this is considered f of u, g prime of the x dx is du, becomes the integral of f of u du, or capital F of u plus c, or capital F of g of x plus a constant. This is known as the substitution rule, everybody. For example, the integral of 2x, parentheses x squared plus 5 quantity cubed dx. The tip is look for a function u equals g of x anywhere in the integrand, and its derivative du, or g prime of x, multiplied by dx. We are dealing with a couple of polynomials. One of them is 2x, one of them is x squared plus 5. The more complicated one in this case is x squared plus 5, and therefore that's the choice of you. You know, if you differentiate it, du dx becomes 2x. Therefore, du is 2x dx. We are going to rewrite this, so it becomes obvious. This piece, so I'm going to put the 2x next to dx. This piece is u, this piece is du. What we have is u cubed du, and that uses the power rule, becomes 1 over 4 u to the power of 4 plus a constant. Reverse substitution, 1/4 x squared plus 5 to the power of 4 plus c is the final answer, everybody. That's how we arrive at the answer using the substitution method. This is another example. Again, we are dealing with a bunch of polynomials. The more complicated one is x cubed plus 1. And you notice the derivative of that is 3x squared. So note that 3x squared is the derivative of x cubed plus 1. Therefore, we are going to rewrite this in the following manner. By writing 3x squared next to dx, and we do the substitution by letting u represent x cubed plus 1. Next to it, this entire thing, 3x squared dx, is du. And so this integral becomes u to the power of 10 du. Using the power rule, we get 1 over 11, u to the power of 11, and a constant. Reversing the substitution, becomes x cubed plus 1 to the power of 11 over 11 plus the constant. Any constant will do. Same thing here. Notice you're dealing with a couple of polynomials. This is more complicated. That's the choice of u, and therefore we write u is x squared plus 3x plus 5. The derivative is 2x plus 3. That means du is 2x plus 3 times dx. You don't have to move anything. Just notice this is u. 2x plus 3 dx is du. So we have 9u du. By the way, number 9, in or outside, the integral sign makes no difference. So you're really dealing with u, and you're going to use the power also, which is half of u squared. So 9 halves u squared plus a constant. U is replaced, and we get 9 halves x squared plus 3x plus 5 to the power of 2 plus a constant, and we're done. What happens when we have fractional formats? Number one, can I simplify a fraction because it has to be put in its lowest term? If you can, you must. Number two, if you can't, the denominator, even if it has an exponent without the exponent, is the choice of u. In this case, 5 plus e to the power of t. As you know, the derivative is e to the power of t, therefore du is e to the power of t dt. Now, it's important to know when you read this, dt is a part of the numerator. In other words, it's e to the power of t times dt over 5 plus e to the power of t. And we're going to write it in this fashion. So it becomes clear that you are dealing with du over u. And that is a simple case of it. Natural log. So you get ln of absolute value of u plus a constant. And you replace the u with 5 plus e to the power of t. And because 5 plus e to the power of t is positive, I hope you remember e to the power of t, the range is from 0 to infinity. 0 is not included. So this is larger than or equal to 5. You can drop the absolute value and change it to parentheses if you like. In this case, the first step is, can I simplify? And the answer is no. How do you know you can't simplify? I want to make sure everybody understands what's going on. So, reminding you of the quadratic formula, ax squared plus bx plus c equal to 0. X is minus b plus minus a squared of b squared minus 4ac over 2a. The discriminant is b squared minus 4ac. Why is it called a discriminant? Because it gives you a lot of information. When it's positive, it has two distinct real solutions. When it's one real solution, rational, of course. And if it's negative, we have no real solutions. Instead, we have two complex solutions, a plus minus bi. Furthermore, if b squared minus 4ac is a perfect square number, then this can be factored. So as we look at the denominator here, take a look. This one, a is 1, b is 2, c is negative 1. So b squared minus 4ac is 2 squared minus 4 times 1 times negative 1, positive 8. Is 8 a perfect square number? No, therefore it can't be factored. Now, even if we can factor, it has to have a factor of x plus 1, so it can be simplified. So even if it can be factored and it doesn't have x plus 1 as a factor, there is nothing we can do. Therefore, pay attention to both cases that I just mentioned. The denominator is a choice of u. As you know, its derivative, du dx is 2x plus 2, or 2 times x plus 1. Therefore, du is 2 times x plus 1 dx. We are going to rewrite this by putting the dx next to the numerator. And as I've mentioned before, you can solve for dx, but in general, if a number is missing, okay, as it's the case here, you can throw in the number and undo it with its reciprocal. So you can put that here, and you can only do it with numbers. Again, in most texts, they solve for dx. This is a much easier way. Plug in 2, 1/2, out. Out or in, it makes no difference. As long as their product is positive 1. The reciprocal of 2 is 1/2. So in essence, you're not changing anything, except it makes life easier. Now you have du over u. And again, just like this one is a natural log, so 1/2 natural log of u plus a constant. Replace the u, and we're done. Now, this is 1/2 ln of absolute value of x squared plus 2x minus 1 plus c. Because this can be positive or negative, you have to keep the absolute value. This one, if you lose the absolute value, it's fine, no problem. Now, what if we have the reciprocal of one of them, and it works in the same manner? If you have the reciprocal of this one, you have to do long division and work on it. If you have the reciprocal of this one, all you have to do, make up 2 fractions. This one is 5 e to the power of negative t, and this one is just 1. So the integral is 5, okay, divided by negative 1, minus 5 e to the power minus t plus t and a constant. And that means you need substitution here. You don't need substitution here. Don't mix them up. What if we have e to some power? It is always the exponent that is the choice of u. In this case, x to the power of 5. Its derivative is 5x to the power of 4, which makes du 5x to the power of 4 dx. Let's rewrite. And what we are dealing with here is e to the power of u du. Simple case. The answer is itself, e to the power of u and a constant. U is replaced with x to the power of 5, and we're done. In this case, the integral of x to the power of 4, e to the power of x to the power of 5 minus 2. Again, the exponent is the choice of u. The derivative again is 5x to the power of 4, just like this one, which makes du the same thing, 5x to the power of 4 dx. Now, to become clear what we are dealing with, again, I'm going to move x to the power of 4 and put it next to dx. So when I compare it to du, I see a number is missing, 5. Again, you can solve for dx, or take the easy way out, plug in 5, undo it with its reciprocal 1/5. And now you notice that you have a 1/5 e to the power of u du. Again, the same as this one, of course, with 1/5. So you write 150 to the power of u plus a constant. Replace the u, and we are done. 150 to the power of x to the power of 5 minus 2 plus a constant. Bear in mind, as always, take the derivative of this, you get this one without the dx. Take the derivative of this one, you get this one without the dx. So you can check your work with the reverse process, namely differentiation of the result. So as I mentioned, in most texts, including yours, they solve for dx. So in this example, I'm going to do it both ways. Okay. The choice of u would be the polynomial 3x plus 7. We know the derivative is 3. Therefore, du is 3 dx. We're going to solve for dx. We're going to do it by the method that your book does, just because it really doesn't make that much of a difference. So I want to show you both methods. And that's not the method I use. Dx is du divided by 3. So this, you write it, and it becomes square root of u. This dx is du over 3. And again, because we want to integrate, we're going to write this as u to the power of 1/2, and 1/3, we're going to take it out. Please understand these two are the same. And we can move on from here. The way I do this is to just rewrite this. I'll go through this process, and I'm going to stop here. And when I compare, I notice everything is in order except number 3 is missing. So I'm going to put number 3 and its reciprocal 1/3. And that's exactly what we have here. I believe this is a tad faster and it's easier. In any event, 1/3 remains. This is 1 over 1/2 plus 1, u to the power of 1/2 plus 1, and a constant. Again, this has been done. A number of times. This is 3/2, and therefore this is 2/3. The product of these two is 2 over 9. 2 over 9. And u to the power of 3/2, replace the u, and you're done. You could put it in the same format, in which case you get 2 over 9 square root of 3x plus 7 cubed plus a constant. You can do that. And that exponent, everyone, you can put it inside or outside the radical. Makes no difference. It has the same meaning. So a quick recap. When I'm integrating this and I see du that has a multiplier, a coefficient 3, I just throw in 3 and undo it with 1/3. Your text solves for dx. I think it's a tad more complicated, especially if this du is involved. But it's your choice as long as you follow those steps. By the way, when you do substitution for your homework assignments, for your exam, the very first thing is to give your reader the choice of u, and therefore you come up with du as well. You have to show that, okay? The u substitution. The first one is ln x to the power of 2x dx. We want to integrate. The second one is dx over x ln x. We want to integrate that. And both of them involve ln x. So let u be ln x. Anytime ln x is involved, almost always the choice of u is ln x. So what is the derivative of ln x is 1 over x. So what is du? 1 over x dx. Now 1 over x dx, I can write it as 1 over x dx or dx over x. And I do that because in case you come across this format, that means the same thing. So I highly recommend you rewrite the questions that are given to you always in a format so you can separate one from the other. In other words, this is ln x to the second power times 1 over x dx. By the way, dx always belongs to the numerator, okay? Why are we separating in this format? This is clearly u squared du. Power rule tells us this is 1/3 u cubed plus a constant. Replacing it with ln x, we get 1/3 ln of x to the power of 3. Please understand this is ln x times ln x 3 times. Do not mix up these two. This is not equal to this, okay? Because this means 3 ln x, okay? This means ln x times itself 3 times. So the notation is important. Make sure you have the proper notation, everybody. For the second case, we are going to rewrite it so it becomes clear what we are dealing with. It's 1 over ln x times dx over x. On purpose, over here I put 1 over x dx, over here I put dx over x just to emphasize, okay, this and this are both the same. So not a big deal. So this is 1 over u and this is du. Now 1 over u follows the log. So this itself is a log. So ln of absolute value of u plus a constant where u itself is ln x. So you say ln of absolute value of ln x plus c, and absolute value must remain because no one take a chance ln x can be positive or negative, remember. The range is all real numbers. All right, for ln x. That's why you put in an absolute value. We want to evaluate these integrals, and I want you to see them side by side, again, for comparison. We are dealing with sinusoidal functions. Trigonometric functions involving sine and cosine are called sinusoidal functions. And so in this case, it is the argument of sine that has the exponent, therefore that is the choice of u. If you differentiate that, you get 2x, which means du is 2x dx. So I'm going to rewrite this again to make sure the reader can see what we are given. This is sine of u, but this is not du. Why not? Number 2 is missing. Again, you could solve for dx and move on. But the easier course of action, number 2, just it's a number. You can't do that with anything else. With x, with dx, you just can't do it with numbers. 2 is missing, plug in. Undo it with its reciprocal, 1/2. So you throw in 2 as well as 1/2. By the way, again, even if you put the 1/2 inside the integral sign, it makes no difference. It's a multiplier, it's a coefficient, it remains. So you're dealing with 1/2 the integral of sine u du. The derivative is cosine, but the integral of sine is negative cosine. So this gives you negative cosine. So you get minus 1/2 cosine u plus a constant. And cosine u means cosine of x squared. So minus 1/2 cosine x squared plus a constant. As always, if you differentiate the result, you get the same thing back without the dx. So what's the difference here? This one has one of them, either sine or cosine. This has both sine and cosine. In which case, the one which has the exponent without the exponent is the choice of u. What's the derivative? In other words, the u dx is cosine x, therefore the u is cosine x dx. Rewrite it as u squared du. Following the power rule, we get 1/3 u cubed plus a constant. Replace it with sine x. We get 1/3 sine cubed x plus a constant. And we're done. As always, differentiation will result in the same thing without the dx for checking. What about the case where cosine has the exponent? The integral of cosine to the power of 20th x sine x dx. Obviously, cosine x is the choice of u. So what is the derivative? Minus sine x. Therefore, the u is minus sine x dx. So we notice we have everything except this guy is not this guy. What's missing? Negative sign. So I can put this inside the parentheses, put a negative in and a negative out. The product of these two negative signs is positive 1, and we are fine. Now I have u to the power of 20 du. Of course, the negative remains outside or inside, makes no difference at this point. This is 1/21, u to the power of 21 and a constant. Again, we keep the negative sign. So negative 1/21 u to the power of 21 plus a constant, where u is replaced by cosine. And the final answer is negative 1/21 cosine to the power of 21x plus a constant. So let's recap. When the argument has a power, that's the choice of u. When sine has a power and cosine is there also, sine without the choice of u, without the exponent is the choice of u. When cosine has the exponent, cosine is the choice of u. Okay. Now, substitution for definite integrals, the integral of a to b, a is 1, b is 2, 2x times x squared minus 1 quantity cubed dx. How do we do that? Well, there are two methods. One of them is to return to the original variable, meaning finish the job if you have to. This is when it's done by substitution. You finish the job and you go back to the original variable, and original limits are 1 and 2. So in this case, if You choose the more complicated one, in this case, x squared minus 1. You know the derivative is 2x, therefore du is 2x dx. So if I move the 2x, you notice that we have u cubed du. So we are going to write it. However, the limits that were originally 1 and 2 are no longer here because the limits are different. So what are the new limits? Well, returning to the original variable, you can ignore it. You don't even have to evaluate it. We will finish that and we look at the second case. So this is 1/4 u to the power of 4. Again, doesn't matter what the limits are because we are going to go back to the original variable and we're going to write 1/4 x squared minus 1 to the power of 4 from 1 to 2. That's why if you ignore it, it doesn't matter, everybody. So if I plug in 2, I get 4. 2 squared is 4. Minus 1, I get 3. 3 to the power of 4 is 81. If I plug in 1, 1 squared, 1 minus 1 is 0. So to the power of 4 is 0. So I get 1/4 81 minus 0, 81 over 4, and I'm done. That's it. You can always go back to the original variable. However, the second method is to keep track and figure out what the new limits are. And bear in mind, this is u. So if I put the upper limit as well as lower limit, I can figure out the new limits. For example, the lower limit, a equals 1. If I put in here, I get 1 squared minus 1 is 0. The upper limit in this case is 2. If I put 2 here, 2 squared minus 1, 4 minus 1 is 3. So I can say this is the same as this with the limits that we just found, 0 to 3. And if you plug, and normally this is easier to evaluate. If I plug in 3, I get 3 to the power of 4, 81 over 4, 0 is 0. So I hope you see this is a tad faster. So it gives rise to the following theorem. If g prime of x is a continuous function on the closed interval of a to b and f is continuous on the range of u equals g of x, then the integral of a to b f of g of x g prime of x dx equals the integral of f of u du evaluated from g of a to g of b. Again, what does it mean? Just plug in the lower limit into the u and the upper limit into the u to figure out the two new limits. That's all. That's all it means. We want to evaluate the integral of 3 to 4 x squared of 25 minus x squared dx. So this 25 minus x squared to the power of 1/2. 25 minus x squared is the more complicated polynomial than x. Therefore, that is the choice of u. Its derivative, it's negative 2x. Du is negative 2x dx. Let's move things around by putting x next to dx. And as we compare, we see everything is in order except minus 2 is missing. And therefore, because it's a number, I can throw in minus 2 and undo it with its reciprocal minus 1/2. Again, please understand the product of the two numbers must be positive 1 and positive 1 only. And it is. So we have negative 1/2 square root of u du. And what are the new limits? Let's work on them in a moment. This we've done a number of times. This is u to the power of 1/2. This remains. U to the power of 1/2 is 1 over 1/2 plus 1. U to the power of 1/2 plus 1. Again, has been done many times. 1/2 plus 1, 3/2. 1 over that means the reciprocal of that is 2/3 times negative 1/2, negative 1/3. Therefore, we can go back to the original variable and write down minus 1/3. U is replaced by 25 minus x squared to the power of 3/2 from the original variable 3 to 4. Original limits 3 to 4. Or we can figure out the new limits. So we're going to plug in number 3. When I square it, I get 9. 25 minus 9 is 16. I can plug in 4. Squared, I get 16. 25 minus 16 is 9. And those are the new limits, everybody. So I'm going to plug in 9. I'm going to plug in 16. And I'm going to evaluate it. I'm going to keep the negative 1/3 out. So 9 to the power of 3/2 minus 16 to the power of 3/2. And in front, we have negative 1/3. 9 to the power of 3/2 means square root of 9. 3 cubed 27. 16 to the power of 3/2 means square root of 16. 4 cubed 64 minus 27 minus 64 negative 37 times negative 1/3 is positive 37/3, and that's the final answer, everybody. We want to evaluate the integral of 0 to 2x squared 2x cubed minus 8 quantity cubed. We have polynomials. This is more complicated. The parenthesis 2x cubed minus 8, that is the choice solution. So du becomes 6x squared dx. So let's move the x squared next to dx. Again, it becomes clear what we are dealing with. So this is u cubed, but this is not du. Remember, you can solve for dx, but an easy way would be to plug in number 6, undo it with its reciprocal 1/6. So you can do that again with numbers. So we do it. And now we are dealing with 1/6 u cubed du, and I'm not going to write the limits yet, but we need to figure it out. So if I plug in 0, it becomes 2 times 0 cubed becomes minus 8. The lower limit is minus 8. If I plug in 2, I get 2 times 2 cubed minus 8. 2 cubed is 8 times 2 is 16. 16 minus 8 is 8. So from negative 8 to positive 8, those are the new limits. Now u cubed becomes 1/4 u to the power of 4. That 1/6 remains outside. And so The product of these two is 1 over 24. We're going to keep it outside. U to the power of 4 from minus 8 to 8. Or we're going to replace the u with 2x cubed minus 8 from 0 to 2. Now, you can evaluate it here using the limits 0 and 2, or evaluate it here using the limits minus 8 and 8. This is easier, everybody. In fact, let me quickly show you. So we get, for this part, of course, 1 over 24 remains, okay? For this part, we get 8 to the power of 4 minus negative 8 to the power of 4. Because the exponent is even here. Minus 8 to the power of 4 is the same as 8 to the power of 4. So this is the same as 8 to the power of 4. They cancel each other and we get 0. And again, by the way, if it's odd, that's not happens. That's not what is going to happen. This becomes minus, and this 8 to the power of, if it's, for example, 3 become minus 8 to the power of 3 remains negative. Negative times negative becomes positive. Two different things. However, it's easier to evaluate it here. I hope you see that than here. Okay. Either way is fine. The rate of growth of a fish population was modeled by the equation g of t is 30,000 e to the power of negative 0.60 over 1 plus 5 e to the power of negative 0.60 quantity squared, where t is measured in years since 2000 and lowercase g of t in kilograms per year. If the biomass was 40,000 kilograms in the year 2000, what is the predicted biomass for the year 2020? Round your answer to the nearest whole number. Well, this represents the derivative. So capital G of t, if capital G of t represents the biomass of fish at time t, then the growth rate is its derivative. Capital G prime of t equals lowercase g of t equals to this function that was mentioned. And what is this? This is the initial value. G of 0 is 40,000. The year 2000 is the beginning. The beginning is considered t equals 0. So based on the accumulated change, also the net change theorem, the amount of increase follows the integral of this over the course of 20 years, the first 20 years from 0 to 20. The integral of 0 to 20, g of t dt, replace the g of t. And to work on this, we need substitution. So the very first thing is, when you have a fraction, can I simplify it? Since we can, the denominator without the exponent 2 is the choice of u. So how do you differentiate this? First, I want to look at u prime, or du dt is just 5 times negative 0.6 times e to the power of negative 0.6 t. The product of these two obviously is negative 3, which makes the u the same thing, negative 3 to the power minus 0.6 t dt. Now, as we look at the given, we notice the bottom is u squared, the top is, well, we are looking for negative 3 and we don't have it. Well, two choices. Take the 30,000 out and then say, okay, multiply by negative 3, divide by negative 3. Or notice we can divide 30,000 by negative 3. It's divisible by it, and it's the product of negative 3 that we keep and negative 10,000 that we take outside. Why do we do that? Because we want it to be clear that this one is negative 10,000, so be it, but this is du. The numerator is du. The denominator is u squared. And I'm not going to write the new limits yet. We're going to come up with that in a moment, but you can always go back to the original one, and the original limits 0 to 20 but we're going to discuss the new limits in a moment. So this is negative 10,000. D over U squared has been done many, many, many times. This is U to the power of minus 2 du, which uses the power rule, and it becomes 1 over negative 2 plus 1, U to the power of negative 2 plus 1. Minus 2 and 1 is minus 1. 1 over that is minus, and this is U to the power of negative 1. So we have negative 10,000 minus U to the power of negative 1. Okay? So again, pretty straightforward. Negative times negative is positive. So this is really 10,000, positive 10,000, divided by U. But what are the new limits? Let's figure them out. Let's erase the word. Let's plug in 0. If I put 0 here, I get 1 plus 5, e to the power of 0, which is 1, and it becomes 6. If I put 20 here, I get 1 plus 5, e to the power of negative 0.6 times 20. Their product is negative 12. Therefore, their lower limit, 5 plus 1 is 6. The upper limit, this one is 1 plus 5 e to the power minus 12. So to evaluate, I'm going to take the 10,000 out, and I'm going to say 1 over U. And this is 6. And this one, if you put it into a calculator, for all practical purposes, this is 0 becomes 1, because it's 1.0000, 4 zeros and then 31. So really the top value is 1. So 10,000 times 1 over 1 minus 1 over 6, which is 1 minus 1 6, which is 5 6 times 10,000, and with one decimal, no decimal, whole numbers, becomes 8333, because this is 3 next to it remains unchanged because this is 3. And what about the initial value? Will be added to this number to give us the year 2020 is the sum of the 248,333 kilograms. That would be the biomass. The second method, and we've done this before for a different, of course, a similar question which didn't need the substitution. So instead of taking the integral from 0 to 20, you're going to take the integral in general. And the integral, I'm going to come here and see the answer was 10,000 over U. So that means 10,000 over U plus a constant. That's the meaning of it. And then I'm going to say, therefore, the capital G of t is 10,000 over, I put the U, 1 plus 5 e to the power minus 0.60, plus a constant. And I use the fact that G of 0 equals 40,000 to solve this initial value problem. Remember, this is a general solution. Now, if I replace the t with 0, I get 10,000 over 1 plus 5 plus c equals 40,000. 10,000 divided by 6, subtracted from 40,000, you get 38,333. And G of t is 10,000 over 1 plus 5 e to the power minus 0.60 plus this number. So what do we want? In the year 2020, we want G of 20. And that's exactly the same thing. The advantage, if I want the year 2025, G of 25, 2030, G of 30. That's what makes it nice and easy. So some people prefer it in this manner. Okay, everyone? So a quick recap, this is an application problem where the integral gives you this concept known as accumulated change or the net change theorem, and you evaluate it from A to B. The difference in this case is that we have to go through the substitution method to come up with the answer. Now, I want to look at these questions side by side. The integral of 2x dx over 1 plus x squared versus the integral of 2x dx 1 plus x squared quantity squared. And what I want to emphasize is when you integrate, of course, this happened to be a rational function, but any fractional format after, of course, simplifying it, the denominator is a choice of u, but if the denominator has the exponent, it is the choice of u without the exponent, okay? And so with that being the case, if u is 1 plus x squared, du dx is 2x, and du is 2x dx. So rewrite it as the integral of du over u. So the answer is a natural log. So natural log of u plus a constant. Replace the u, and because u is positive, in fact, it's always larger than or equal to 1, you can drop the absolute value and make it ln of parentheses 1 plus x squared plus a constant. In this case, you get du over u squared. In other words, I'm going to use exactly the same u substitution. And this, we have done it many, many, many times. We bring it up, so we make it ready for the power rule. So the integral of u to the power of minus 2 du, we say 1 over negative 2 plus 1, u to the power of negative 2 plus 1 plus a constant. Now, of course, minus 2 and 1, they add up to negative 1. So this is negative 1. And this is 1 over negative 1, which is negative 1. So you're dealing with negative 1 over u. So negative 1 over, replace the u with 1 plus x squared, minus 1 over 1 plus x squared plus a constant. So to compare and contrast, this one, when it doesn't have an exponent, ends up, you have the same u and du. This ends up being a natural log. But when it has an exponent, doesn't matter what number and how large, since you bring it up and you make it negative, ultimately uses the power rule. So it won't be a natural law. This question, some of you will just learn this in the future, at least that you can easily see the answer, but for now, definitely surely use u substitution. And by the way, when you, again, substitution, first thing first you do, you use the u substitution and you show your reader what is the u that you're using. In this case, is x plus 3. And then you tell your reader du is dx because du dx is just 1. So that's the beginning before you move on to the next step. So it's the integral of du over u, which is going to result in a natural log of u plus a constant. You replace it with x plus 3, and you get ln of absolute value of x plus 3 plus a constant. The difference here, 1 plus x squared is positive. You can lose the absolute value sign and change it to a parenthesis. But this one you can't and you shouldn't, because x plus 3 can be positive or negative.